So now it's time to do some trigonometry because we kept saying algebra and trig, but we never did a trig one. So I feel that we need one. So let's check our form here. We're taking the tangent of theta to the cosine of theta, and it's the limit as theta approaches 3 pi over 2 from the negative side. Okay, so let's think about that. We're taking the tangent of theta. Tangent is sine over cosine, right? So let's draw a little unit circle real quick. Okay, 3 pi over 2 is right down here. So I want to approach 3 pi over 2, right? And as I approach 3 pi over 2, the tangent of 3 pi over 2 is, let me write it, tangent of 3 pi over 2, because this is over 0 down -1, right? So the tangent of 3 pi over 2 would be -1 over 0, which is infinity. I mean, it could be negative infinity. It doesn't really matter, right? It's infinity. Okay, so then that means that I know that my form is infinity to the, okay, cosine of 3 pi over 2 is 0. So it's infinity to 0, which is indeterminate. Yet again, we have another indeterminate form. This is the third type. Remember, there are 3 types of indeterminate forms that use this method. 1 to the infinity, we did that one on this page, 0 to the 0, which was that example, and then infinity to the 0, which is this last one. Infinity to 0 isn't necessarily harder or easier. I just have a feeling trigonometry is not going to be your favorite thing ever. All right, so step 1, I'll set L equal to this limit as theta goes to 3 pi over 2 from below of tangent of theta to the cosine of theta. All right, so there's step 1. Step 2, we will now take the natural log of everything. So the natural log of L equals the limit as theta goes to 3 pi over 2 from below, from lesser values, of the natural log of tangent of theta to the cosine of theta. And then at this point, we are going to use algebra, trigonometry, everything. So this is the natural log of L equals, bring the cosine, so the limit as theta goes to 3 pi over 2 from below of the cosine of theta times the natural log of the tangent of theta. And we're going to keep using that algebra trick, but I'm going to use it right here. So remember that 1 over 1x? So I'll just make a little note. Algebra trick. It's an algebra trick even though it's with cosine, which is that the cosine of theta is 1 over the cosine. We keep doing it with x, but you can actually do it with kind of anything. So this is equal to the limit as theta goes to 3 pi over 2 from below of the natural log of the tangent of theta over 1 over the cosine of theta. Okay, how in the world is that helpful? Well, because that's the limit as theta goes to 3 pi over 2 from below of the natural log of the tangent of theta over 1 over the cosine is the secant of theta. Let's check our form. Let's see where we're at. So check form. We have the natural log of infinity, right? Because the tangent of theta is infinity. We proved that right up here. So natural log of infinity over 1 over 0, right? Because secant is 1 over the cosine. So that's 1 over 0. So that would be infinity over infinity. Yay! Because then we can use L'Hopital's rule. And I'm running out of space to use L'Hopital's rule. So L'Hopital's rule, I think I'll go horizontal here. That's the limit as theta goes to 3 pi over 2 of tangent is, you see, natural log of tangent is 1 over tangent of theta. Derivative of tangent is secant squared of theta over the derivative of secant is secant theta tangent theta. Well, obviously some of that cancels. So that's equal to, I mean, one of the secants is going to cancel with that secant. The tangent, tangent doesn't cancel, sorry. The tangent becomes tangent squared because that's in the denominator, so sorry. So this is the limit as theta goes to 3 pi over 2 from the negative side of, there's one secant left on top, there's a tangent and another tangent, so it's tangent squared. Okay, so let's use all of our knowledge and tricks here. Now at this point we actually have a couple options available to us. We can mess around with secant and tangent. We actually have a lot of identities, so we could make these cosines and sines and all of that good stuff. So if you wanted to turn this one secant into 1 over cosine and this is sine squared over cosine squared, you could do that. But let's think about our form for just a second. So if I look at this, the secant of theta, I just did that right here, it's infinity. And the tangent of theta is infinity squared. So that's infinity over infinity, which means I could do another application of L'Hopital's rule. And I'm going to. So I'm just going to make this purple. L'Hopital's rule, another time. So that would be the limit as theta goes to 3 pi over 2. Derivative of secant is secant tangent. Derivative of tangent squared would be 2 tangent times the derivative of tangent, which is secant squared. All right, now what cancels here? The tangents are obviously gone. The secant is gone. So one of the secants, I should say. So this is the limit as theta goes to 3 pi over 2 from below of 1 divided by 2 secant theta. All right, well, secant's a little weird. I mean, it's not quite what we're used to. So we could say that is the limit as theta goes to 3 pi over 2 of the 2 stays down, but the secant is 1 over cosine, so it's cosine theta divided by 2. Now, cosine theta is not indeterminate. We know what cosine of theta is. If I get that, it's 0, right? So this would be 0 over 2, which is 0. So then that means that we're now ready for step 4. All of this work was step 3. Step 4, the natural log of L is 0. So L is e to the natural log of L, which is e to the 0, which is 1. And you can see it right here. The graph, as you approach 3 pi over 2 from below, is going to 1. Right there. You'll notice this is a function that only exists from 0 pi over 2 to 0 to pi over 2 and pi to 3 pi over 2. That's because 0 to pi over 2 is quadrant 1 and pi to 3 pi over 2 is quadrant 3. If you look at the tower function, tangent has to be positive. So the two quadrants where the tangent would be negative don't exist because that's not a function that Desmos can graph. It's not a function. So that's why that function disappears in there. And that's why we have to approach from the negative. That's why it's so important to put the negative everywhere, because we actually cannot approach from the positive side. The function doesn't exist there. Looking back over all of our work, we've used this particular trick multiple times. We used some trig identities in here, as well as that little algebra trick right there. We checked our forms regularly, and when you got to here, you actually have choices. So you either can use a bunch of trig identities if you want to avoid L'Hopital's rule, but L'Hopital's rule is actually easier than doing all the trig identities, in my personal opinion. And then you use another L'Hopital's rule, everything sort of cancels out, and there you are at the end. So you're using some trig identities, and as well as L'Hopital's rule, as well as algebra, to finally come up with your result.